So here's something that's never discussed in astronomy. Why does Saturn, Neptune, Uranus, Earth, Mars, Venus, Mercury, Jupiter, the Sun, TRAPPIST-1, Lune Star, Proxima Centauri, why do they all spin? Why are they all spinning at different rates as well? Long story short, they spin because they're stars in various stages of evolution. The astronomers, I wanted them to understand what it is they were doing. That's one reason why I started working on this theory feverishly. Is that I wanted people to know, especially the astronomers, to know that the stars, they are one and the same to planets. Our words are what confusing them. And we know this because we can literally date these objects and find out that they actually are one and the same just by how much axial angular momentum they have. So the Sun's really young. There's T-Garden star, there's TRAPPIST-1, Lune star, Proxima Centauri, Jupiter's down here, Saturn, Neptune, Uranus about the same age, Earth, Mars, Venus, Mercury. And as you can see, it all goes down. So you have your young, bright, hot stars over here, and then it moves down sort of more of an area. I have written down here, it's not a smooth line, but more of an area. The dotted line is the line of best fit, and the smooth lines give margin of error. This is subject to revision. Now it's very rough, but the dotted line is the line of best fit, and the smooth line is error margin. So you could have objects all inside of that area between those solid lines, and that's where the objects are in our system and obviously other systems. I have here, it's important to know this. It's important to know why the planets spin. They're old stars that have lost most of their mass, thus most of their angular momentum. And some stars spin with more axial angular momentum because they're younger. They've had more time, they've had less time, I should say, to have winded down and to have lost their mass. And I have here axial angular momentum loss due to mass loss at different rates. So not only do they lose their mass, but the mass can be lost at different rates as well. You see how Jupiter falls below that solid line? That means it was in orbit around a younger, hotter star for a short amount of time, and then Saturn's beneath it too. Now, this isn't the WT diagram, this is the axial angular momentum. So, on the y-axis, you have the age in years. So it gets much older as you go down logarithmically. So you have, where's Earth? Earth at 4.5 billion. Earth 4.5 billion, Mars between 40 and 25 billion. And you have, which star is that? That's, yeah, Mars, and then Venus and Mercury. So there's Venus and there's Mercury. And Mercury I have between 7 and 21 trillion years old. So far, far, far older than what the Big Bang pundits allow. And that's basically it for that. I didn't publish, that's on paper 436, I believe. I didn't put this in another paper, but basically to read this out, that highlighted area is tangential velocity, which means on the surface of the object, or if it doesn't have a surface, on the very, very edge of where the atmosphere interacts with outer space, the tangential velocity is how fast it's going. Not the total axial angular momentum, and not the rate at which it spins at. Tangential velocity. The tangential velocity of Earth at the equator is about 1,100 miles an hour, something like that. But the tangential velocity goes down linearly, and then you have time, which is the x-axis, and then you have on the y-axis the total axial angular momentum. So you have high total axial angular momentum, and it decreases as it expands. So the star starts out really, really small, and it spins extremely rapidly with a lot of mass, and then it expands outwards and it slows down. Think of that experiment or a demonstration when you have an ice skater spinning and their hands are tucked in tight. And then when they expand their arms out, they slow down. So that's what's happening. When the star is born, it starts out really, really small. It expands outwards, it slows down, but then it starts to gravitationally collapse. And during this gravitational collapse process, it loses mass. So the tangential velocity will go up, and the time obviously gets older, but the total axial momentum will go up as well. Gosh, I need to work that out. I can't remember why I put on the y-axis. But anyways, so it expands outwards, and then it gravitationally collapses. It reaches a peak right here, and then it comes back down again slowly over many billions of years. And eventually it stops spinning altogether. This needs to be worked out a lot more. I just stopped doing it because, well, to be honest, I need more information. I need a lot more spin rates for the brown dwarfs and the red dwarfs and their masses, and I need all the masses and spin rates of the exoplanets, which are just more evolved stars, and all of them are going to fit on this graph somewhere. So what this means is we're never going to see a gas giant star that's not spinning. You're not going to have one tidally locked because they're too young. Jupiter is what, 700 million? Saturn is 550 million. Neptune and Uranus are between 1.1 and 1.2 billion. If you're going to have anything tidally locked, it's going to be a rocky object. It's going to be something like Ganymede sized, or at the very most Venus or Earth sized. And anything much bigger than that, it's just too massive. There's so much spin from when it was much younger. It's not going to be it can be tidally locked to a younger, hotter star. It can slow down though, and that's the whole point. Axial angular momentum loss due to tidal interactions and impacts really starts about where Earth is. So if Earth were to take up orbit around the sun, be really close, like the ultra short period planets, it could slow down tremendously, and then well, just stop spinning. And that's where Venus is right now. Venus is basically stopped spinning. It's almost tidally locked. I mean, I think it spins about the same rate as which it orbits the sun, which is very unique. They say Earth and Venus are twins, but there's no way. Venus is far older than the Earth, which is evidenced by its surface features, the lack of magnetic field, the fact that it no longer spins. When you have no friction in outer space with the atmosphere to outer space, if you spin something up, it's going to keep on spinning. The only way to get something to stop spinning in outer space is to make it tidally interact with another object. So you have a much larger, more massive object like the sun, something spinning around it that's smaller. The gravitational fields of both these objects are gonna force there to be friction inside the actual smaller object. There's gonna be friction in there. It's gonna heat it up, and it's gonna think like a magnet. If you have two magnets like in orbit around each other, those magnetic fields are going to run a line, and then eventually they're going to align with each other. They're not going to be spinning anymore. But I guess that's a poor way of explaining it. But anyways, I'm just kind of frustrated how astronomers they don't make these types of connections. I guess it's blasphemy, if you will. But I'm kind of disappointed. Sorry for coughing so much. And as a final note, collapsing stars struggle to maintain their angular momentum as it is conserved during gravitational collapse. But angular momentum only decreases alongside mass decrease. So think in terms of basic physics. If you have something spinning, the only way to get it to stop spinning, especially if there's no friction, is to remove the mass or to remove the tangential velocity, or remove the tangential velocity, you expand it outwards. But to lose the total axial angular momentum, because that's a conserved quantity alongside mass, you have to remove the mass. And luckily, that's exactly what happens with highly evolved stars, is that as they evolve, they lose their mass, therefore they lose their axial angular momentum. It goes hand in hand. All right, guys, I think that sums up this. I'm coughing too much. All right, later. Oh yeah, hi Celeste.